Have you ever really stopped to think about all the invisible code that's basically running our entire modern world? I mean, from the car you're driving to the medical devices that are literally saving lives, there is this hidden layer of software that makes it all tick. So today, we're going to pull back that curtain. We're going to dive into this hidden world of what's called embedded software and figure out what makes it so unbelievably critical.
Okay, so to get us started, I want you to think about this for a second. What do you think is the single most complex part of a modern car? Now, your first thought, it's probably the engine, right? Or maybe the transmission or the suspension system. But you know what? The real answer, it's probably going to surprise you. Yeah, you guessed it, it's not the engine. Nope. It's something way more intricate and, honestly, in a lot of ways, much more critical to how the car actually works, day in and day out. The answer? It's the software. Get this, a single modern car can have over 100 of these little boxes inside it. They're called electronic control units, or ECUs for short. Seriously, just think of it like the car's nervous system. It's this huge network of tiny little computers all running millions of lines of code, and they're all talking to each other in real time. It's wild. And look, an ECU is not like the processor in your laptop that can do a million different things. No way. Each one is a super specialized device. It's a tiny little integrated circuit with its own processor, its own memory, and its own way to talk to other parts of the car. And it's designed to do just one job, but to do it perfectly, whether that's managing the engine's fuel injection or deploying an airbag in literally a fraction of a second. Okay, so when you've got all this incredibly complex code controlling everything, I mean, we're talking about our brakes, our steering, the most important question just jumps right out, doesn't it? How on earth do you make it all safe? And that right there is the core challenge of all mission-critical software. Well, one of the key technologies here is something called sensor fusion. It's a pretty cool concept. Think about it. A car's camera can get totally blinded by the sun, right? And its radar might get confused by something simple like a metal fence. But by combining or fusing the data from all these different sensors, the system can create a much more accurate and reliable picture of what's going on around it. It's a perfect example of redundancy. If one sensor fails, the whole system doesn't just crash. And that brings us right back to the most crucial point. Look, it's one thing to make all this cool tech work. It's a completely different challenge to guarantee that it works safely every single time, no matter what the conditions are. So how do engineers actually build that level of trust right into the code itself? The answer really boils down to incredibly rigorous standards. And the big one in the car world is called ISO 26262. Now, this isn't just a friendly suggestion or a best practice. Nope, it's a mandatory international standard for the entire auto industry. It gives them a super strict framework for the whole development process, from start to finish, and it basically forces teams to think about every possible hazard and then design the software specifically to prevent those bad things from ever happening. Now, a core piece of that standard is this classification system called ASPICE. That stands for Automotive Safety Integrity Levels. Basically, every single software function in the car gets a rating, from A to D. So something like the software that controls your radio, that might be ASLA, least critical. But the code that controls your brakes, oh yeah, that is ASLD, the absolute most critical level. And it has to meet the highest possible standards for safety and reliability, no exceptions. So how do they actually ensure that level of safety? Well, it's definitely not something you just check at the very end. It's built in from the ground up, right from the beginning through layers of rigorous testing. It starts with what's called unit testing. That's where they test the tiniest little pieces of code all by themselves. Then comes integration testing, where they make sure all those little pieces can talk to each other correctly. And finally, you have system testing, where they test the whole car, the entire system, to make sure everything works together just like it's supposed to. And I just love this quote because it really shows you that testing isn't just a cold, robotic process of running scripts. It's actually a deeply human thing. It's collaborative. When the developers and the test engineers don't see eye to eye, they don't just go to their corners and argue. They have to negotiate. They have to reach a consensus, and they work together to figure out the best way forward to build a better and, most importantly, a safer product. All right, so it's pretty clear this field is super critical, and it's definitely growing, which of course leads to the next big question. Especially if you're interested in this stuff, how do you actually get a job doing this? What does it really take to crack the embedded systems interview? Now, if you're coming from a more traditional software background, you probably think the answer is obvious, right? You just got to grind out hundreds of those algorithm problems on sites like LeetCode. But is that really the right way to go for a field as specialized as this one? And the straight-out answer is no. A big no. Look, while algorithms are still important, they're not the main event here, not by a long shot. An embedded systems interview goes way, way deeper, and it's testing a completely different set of skills. Just like the quote says, this field it's not quite core electronics, and it's not quite core computer science. It's this perfect blend of both. You can't just know how to write code in a vacuum. You have to understand how that code is going to interact directly with the hardware, with the silicon, the processors, the memory. It truly is a fusion of both worlds. So, this gives you a pretty good idea of the kinds of topics that actually come up. Instead of those super complex algorithms, interviewers are going to focus on the fundamentals. They're going to ask you about core C programming concepts like pointers or what the volatile keyword means. They'll definitely test your ability to do bit manipulation, tinkering with individual bits of data. And they'll really want to see that you get the core operating system concepts that are so critical for making software and hardware play nice together. So, where is all of this going? What's next? Well, the entire world of mission-critical software is being completely transformed by the rise of AI, and specifically by a concept you're going to hear a lot more about, AI at the edge. And we got to remember, this is so much bigger than just cars. The exact same principles of safety and reliability apply to the software that runs our power grids, our high-tech medical devices, and even our defense and aerospace systems. I mean, the stakes are incredibly high no matter which of these industries you look at. Now, as AI gets more and more integrated into everything, the way we prove our skills has to change too. A few years from now, a hiring manager isn't going to be blown away by a long list of online courses you took. What they're really going to want to see is that you've taken that learning and combined it with real, hands-on projects that prove you can actually build something that works. A really smart way to think about this is to break certifications down into two main types. First, you've got what we can call learning certifications. Think Coursera or Hugging Face. These are fantastic for building up your foundational knowledge. But then you have the direct contributor certifications. These are things like the big cloud platform certs from Google, AWS, or Azure. These are the ones that actually help get you hired, because to pass them, you're forced to develop genuine fluency on the platforms where the real work is happening. And it's not just the final product. The tools we use to build this stuff are evolving too. AI isn't just the goal anymore. It's becoming part of the process. You've got AI assistants like Claude that can literally act like a coworker, helping engineers write code, find bugs, and optimize the very software that's going to run these next-generation systems. Which kind of leaves us with one final big thought to chew on. We've journeyed all the way from talking about 100+ computers in a single car to a future that's going to be powered by AI at the edge. So, as our world starts to rely on these more and more complex, more autonomous systems, what do you think becomes the most critical human skill? Is it the technical ability to build the software? Or is it the wisdom to know when and how to actually trust it?